Hi, my name is Callie Chappelle, and welcome to this video about the Puromycin assay for MCDB 427, which is molecular biology at the University of Michigan. Now, before we can understand the Puromycin assay, let's first understand what puromycin is, which I've drawn the chemical structure of right here. So puromycin is an analog to tyrosine tRNA, which I've so handily drawn here. Let's take a quick look at the structure of tyrosine tRNA. Well, first we have the tRNA, where we have this crucifix structure, and at the end of every tRNA, we have the same CCA. So here's the structure of the A, and here's the tyrosine. So this, you'll notice, is pretty close analog to puromycin, where puromycin has the adenosine, which is here, which looks kind of like the end of the tRNA, just doesn't have the rest of the tRNA. It has this OH group instead. And then it has this tyrosine analog. So this is how it resembles tyrosine tRNA. Now, it has two key structural features that make it really important. And the first is this tyrosine mimic, and the second is the fact that it looks like the end of the tRNA, which is this part. And as a result, it can actually bind into the A site of a ribosome. And in fact, it only binds the A site of the ribosome. Now, this is really important when we want to ask questions about what binds where, because puromycin can react with any amino acids or polypeptide that's on a tRNA in the P site, and then it can be transferred onto puromycin, which will then be released, which we can measure, which is pretty cool. So there are a couple of consequences here. The first is because puromycin only binds the A site, if the A site's free, puromycin can bind. However, if a tRNA is in the A site, then puromycin actually cannot bind there. It can't bind. Now let's talk about the closer mechanism of the puromycin release. The first is just what we're starting out with, which is this ribosome where we have amino-acylated tRNA here in the P site, and actually this tRNA actually looks like it has a polypeptide on it. The first thing that we do is actually add puromycin. I know, what a surprise. So we're going to add puromycin, which again I abbreviated like this, and it will come, since the A site's free, into the A site. It'll bind in the A site, and after that, then the second step will be peptidyl transferase, or peptidyl transfer, which is catalyzed by the ribosome. No, that's not how you spell it. To produce this peptidyl puromycin, or this puropeptide. Now, this puropeptide is unstably bound, so it actually falls off the ribosome. And it's the falling off of this peptidyl puromycin, which I'm abbreviating as puropeptide, that we actually measure, because typically, whatever the peptide is, or the polypeptide that we initially have in this tRNA, will have radiolabeled, so this entire thing becomes radiolabeled. Now that we understand the mechanism, let's take a quick look at a summary of what we've learned. So the first question we need to ask ourselves is the peptidyl tRNA bound? And if it's bound in the P site, then that means the A site is free. Therefore, if you ask yourself the next question, which is, can puromycin bind? Yes, it can, because the A site is free. And because it can bind, then peptidyl transferase can occur due to the ribosome, and it will cause a release. Now, if the peptidyl tRNA is bound in the A site, then puromycin cannot bind, because there's something else in the A site. So it cannot bind in the A site, which means that puromycin, if it can't bind in the first place, it can never be attached to the peptide, and therefore the puropeptide will never even be created, and therefore will not be released. Let's talk about an example puromycin experiment. So this sounds all fine and dandy, kind of in theory, but I'm always interested in, well, what does this mean? What does the data look like? So we're going to talk about that now. So the big question for this experiment is, which sites, the A or the P site, do tRNAfmet and tRNAmet bind? Right? So where do they bind in the ribosome? So I've drawn that here. So if we have a ribosome, we have our EP and A sites. Does this general tRNA, which could represent either of these two, does it bind to the P site or the A site? So the method is an in vitro puromycin release assay. Now it's in vitro, so this indicates that these factors, the factors that we're going to be adding, are sufficient to make this reaction work. So the real part here is the puromycin release assay. So the first thing we're going to do is add 35S Met-tRNAmet, which is drawn here, or 35S fMet-tRNAfmet. So they start with radiolabeled Met-tRNAmet or fMet-tRNA aminoacylated tRNAs, and it's the amino acid that's radiolabeled with 35S. After they do that, then they're going to add ribosomes and this AUG sequence. Now, this AUG sequence is just a trinucleotide. It's not a full mRNA, but it's made to approximate a full mRNA. So if I draw a ribosome, well, what would this look like if I draw a ribosome here? We're going to be adding this AUG sequence, like that, and then we're gonna bring these guys in because AUG they knew was a codon for both of these guys. Then they're going to add puromycin and then run the reaction. After that, we're going to separate our aminoacylated puromycin, or our puropeptide. Remember, it's this guy that's getting released that we measure. Let me scoot up here. Our puropeptides, they're going to measure this release, and that's going to be shown in these graphs. Before I move on and talk a little bit more about the details of this experiment, I want to go over some quick nomenclature thing, because this is something that I just fundamentally didn't understand throughout this class, and it's very important. So the way that we write amino-acylated tRNAs is we'll write the amino acid first, and then we'll write the tRNA. So fMet-tRNAfmet means that a fMet-tRNA, which is a special tRNA, has fMet on it, okay? Met-tRNAmet means that Met-tRNA is charged with Met. Okay, here is the critical thing. If you have tRNA-fMet, you have the fMet-tRNA, but it's charged with methionine, okay? It's charged with, not fMet like it normally does, but with Met. So it's like we're taking off the fMet amino acid from tRNA-fMet, and we're replacing it with just Met. Okay? And that is reflected in the nomenclature here. But now let's put that aside and just talk about each of these two tRNAs, charged tRNAs, individually. So let's first talk about what happens when we do this experiment with fMet-tRNAfmet. So remember, this is fMet-tRNA that's charged with fMet. And we see that as time goes on, as we run this reaction, more and more puropeptide is released when the ribosome is present, and relatively little increase of puropeptide release is happening without ribosome. So what does this mean? Well, it means that when we have a ribosome present, we're getting this reaction occurring. Where it means that puromycin must be able to bind to the ribosome, there must be some kind of peptidyltransferase happening, and there has to be some release of this puropeptide, since that's what we're measuring here. And so this is telling us that we are getting a release of puropeptide when the ribosome is present and not when there's no ribosome. Now first let's try to understand the difference between ribosomes and no ribosome. Well, we know that in order for a puropeptide to even be formed, we have to have peptidyltransferase that's occurring. And remember, the thing that does the peptidyltransferase is the ribosome. So if there's no ribosome present, it makes sense that there wouldn't be a very much release of puropeptide. Now if there is a ribosome present, that means that there is a lot of release of puropeptide. Now why might that be? Well, remember how puromycin can get into the ribosome in the first place. Puropeptide release can only happen because puromycin can only bind if the peptidyl tRNA is bound in the P site. So remember, the question here is which site, the A or the P site, does Met-tRNAmet and fMet-tRNAfmet bind? And so if fMet-tRNAfmet results in a puropeptide release, it means that fMet-tRNAfmet must be binding in the P site. So the answer to this question is P site. Where does it bind? In the P site. And remember, it's because if the tRNA was in the P site, puromycin will be able to bind, and thus you'll get a release of the puropeptide due to peptidyltransferase by the ribosome. Let's do the same interpretation, or the same style of interpretation with this one. So we have Met-tRNAmet. And what's going on? I'm sorry, we've got this weird line here. Ignore that. So we don't see a major increase in release of the puropeptide when the ribosome is present. That means that there must be something wrong. Either peptidyltransferase can't occur, or puromycin can't be bound in the first place, or there's some kind of problem with the release. Now, there's no other difference here between the tRNA, so we're guessing it's probably not the release. It's probably not anything with peptidyltransferase because we're using ribosomes in both cases. It must be something to do with binding. And remember that puromycin cannot bind to the ribosome if the A site is not free. So the peptidyl tRNA must be bound to the A site if we're not seeing this release of the most reasonable explanation is the reason why there's no pure peptide release is because puromycin can't bind in the first place, because this peptidyl tRNA, Met-tRNAmet is bound in the A site. And yes, that is the answer. So we would expect this guy to be bound in the A site. Now, the last question the researchers wanted to know was, what's important? Is it what it's charged with? Is it the amino acid that's important? Or is the amino acid that's important? Or is it the tRNA? What determines in what site this charged peptidyl tRNA actually binds in? So what do? They create this hybrid. And that's why I wanted to point out this nomenclature. They create this Met-tRNAfmet hybrid. And what does that mean? They take regular methionine and plop it on a tRNAfmet. So they're putting a non-normal amino acid on this tRNAfmet. That's drawn here, right? Where the tRNA comes from tRNAfmet and the amino acid comes from Met-tRNAmet. And then they do the same experiment and they ask, well, what happens? And they see that there is an increase in pyropeptide release, which means that puromycin can bind. If puromycin can bind, that means that this tRNA must be going into the P site. This tRNA must be going to the P site, so the A site's free, so puromycin can bind. Now, if this is going to the P site, well, is it the Met amino acid or is it the tRNAfmet tRNA that is controlling it? Well, let's see. So if it was the Met amino acid that's controlling where it goes, we would expect it to be most similar to this graph. So we would expect the tRNA to go to the A site. Now, if indeed it is the tRNA that's controlling it, we would expect this graph to look like this graph, right? And the tRNA would go into the P site. Because these two look the most similar, and the thing that's the same between these two is the tRNA, we conclude that it is the tRNA that controls, or that is important to get that fMet-tRNAmet to go to the P site. All right, and the difference in release is due to that. The difference in release between these two indicates that it is to do with the tRNA. I hope that this video is helpful to understand not only the puromycin assay, but one particular application, and I hope to see you in future videos.